Hey everyone, continuing from our previous video, in this one we'll start to make some changes to our default contract that Anchor creates so that we kind of understand how instructions, accounts, and context work in Solana. So as you know, most courses start on Solana. We'll start with a counter contract, which is simply taking an account in Solana and incrementing it whenever somebody creates a transaction. So using the initialize transaction, we first need to allocate this account. So now first let's create a struct which will hold our count variable, and we are using u8 as the type, 8-bit integer for 8-bit unsigned integer, storing like a basic variable for now. And we'll use the anchor magic to specify it as an account. Now, once we have declared this counter struct, we need to allocate it on the blockchain. And this is where this initialize instruction comes to our help. In the initialize context, and this is the context just to remind all of you, it's the same one that's passed inside this initialize instruction. So now we'll just allow the user to pass in our counter struct using an account, and we'll have two parameters to it. One is the info and the other is the counter struct that we defined below. And I'm going to do one more thing, is to specify this info variable inside our struct as well. If you're not familiar with this caret annotation, this essentially denotes lifetimes in Rust. Without going in a lot of detail, what we're trying to say is that this counter variable needs to be in memory at least as long as this initialize struct is inside this memory. And for this particular use case, that is completely fine for now. Once you've defined this, we also need to say that in this initialize instruction, we actually need to create this account on the blockchain. And the way to do it is again use Anchor's magic and specify an account with an init constraint, an init macro. And when I do this init, it actually denotes an error and says that there needs to be a pair. What this means is that every account on the blockchain needs to be paid by someone. And so there needs to be a pair, which is the way we'll specify in our accounts as a signer, because this user also needs to sign this transaction. And again, we'll use the same lifetime parameter as we used for the counter, because the same situation applies. And then we'll simply say that the pair is equal to our pair. So we have specified the pair now, but there is one more error which says that the space must be provided. So now Solana needs to know how much space your account will actually allocate on the blockchain. And the way to specify is simply space is equal to 8, which is like a default discriminator memory that we need to specify for each account, and the actual bytes that the account will use, which in our case is 1, because we only have like 8-bit counter, which essentially occupies 1 byte. So this is the total space that our account will hold. With this, the init instruction error is gone, but now we're seeing an error here which says that there needs to be a system program. Because this account will actually be created via the system program, we need to pass in as an account to our instruction as well. And the way to do it is we say system program is a program with the same lifetime as initialize and of type system. With this, we have specified our system program, and now that error is gone. So the error that we were seeing earlier, now we have a final error which says the pair needs to be specified as mutable, because essentially the account will be written to and the fees will be deducted. The way to specify is again using an anchor's macro and saying that the account is mutable. With that, and let me save this file, we have specified all of the accounts that need to be passed in to actually create this counter struct on the Solana blockchain. with that done, now let's just simply read this account from the context, and the way to do it is let counter, and I'm going to read a mutable copy, and we're going to say context dot accounts dot counter, and I'm going to initialize it to 0. With this, now our initialize instruction is set up. It takes in a context which has all of the accounts that we need. It initializes it using the init parameter here. It takes in the pair, it takes in the space, and then it finally initializes the count as 0. Now let me go to our staker directory and run anchor build to make sure that my program still builds correctly, and it does. Now it's about checking in and testing and make sure that our tests still work. So I go in the test, and right now we're not providing anything, and our tests are not updated. So for that, let's just try to see how to pass in all of these 3 accounts, that we created here. So the way to do it is essentially we have this initialize, but then if I do a dot, I can use the accounts and pass in all of the accounts that we need. So we need a counter account, as you can see in the suggestions. We need a pair account, and we need a system program, right? So now let's see how to get each of these. So counter is just simply, we need to pass in a public key or an address, and then this instruction will actually initialize the space on that address. So let's quickly create a counter address, and the way to do it is to simply use anchor.web3.keyPair.generate. So we created like a key pair with a public and a private key, and for the address we're going to simply pass in the public key. This works. For the pair, we essentially need a wallet which is able to pay for the gas fee, and the way to do it is let's first choose. So we are running in a provider which is essentially providing the context in this local environment. So let's just store it in a local variable. So I'll just take it in here, I'll copy it, and then simply pass in as a provider. And now we can use provider.wallet.public key to actually specify the pair, in which case is the default wallet that comes in from this test setup that Anchor provides. And finally, the system program can simply be saved from doing anchor.web3.systemprogram and .program ID. This is like a program that is automatically available on the Solana blockchain, which allows you to actually initialize all of these accounts. So this way, we have provided all of the information, but then our account also needs to be signed. As we had mentioned that the pair is one of the signers, but that will automatically happen because of the context that you're running it in. But we also need to provide a signer for this counter. And the way to do it is, again, have the signers do this, and then simply pass in our counter as a signer. And this is essentially an account with a key pair, so it'll be, we'll be able to sign it. And that's how we create a transaction. Once we have it, we also need to test if our account was created successfully. And the way to do it is simply do an await on the program and program.account, because it's a program account, and then we can see the counter there. And then I'm going to fetch this account, and so essentially read it from the blockchain at this counter.public key. So as I mentioned before, counter.public key is the address where this account was stored. So essentially with this call, we are reading this data, and then let's store it in a variable called counter data, and let's simply log this counter data. Now let me just go ahead and test and see what happens. So we're running the test suite, it's going in, our test has passed, and you can see that the count has been initialized to 0. And now we can definitely put in all of these asserts and make sure that our initialization worked perfectly. So congratulations, you've been able to create a contract, initialize an account, and then read it from the blockchain. Let's just quickly add one more instruction, to actually update this counter. So to add an instruction, the simpler way is simply do an fn. Let's do pub fn update. Let's pass in a context, which in our case we'll call update ctx. Let's just add ctx for more clarity. And I'm going to pass in the new variable. So let's say data u8. And again, we'll be returning a result. So I'm going to follow the same way that we specified in the initialize instruction. And now I need to define our update context. So let me define it here. I'm going to simply say pub struct update ctx. Again, I'll use the same macros that we used for the instruction above. And what I'm going to say is I need to receive the counter variable. So we're going to use the same format as we defined above. The only thing is this time we don't need to initialize it, but we do need to mutate it. So I'm going to specify as mutable. And we need to actually have a signer who will be signing the account. So again, let's just say pair :signer info. And again, this has to be mutable as well. And finally, what we're going to do is we'll simply read the counter again. Send mute context.accounts.counter, and we're going to set the count as the data that is provided. And we're going to return it OK. So we basically updated, like added a new instruction, took in a new context. This time we also included a variable that you can optionally pass to each of these instructions. We read the counter as was specified in, and then we specified the count to whatever data was provided. Let me save this, run anchor build again, just to make sure that the program is still compiling. It is. Let me go to our tests, and this time let's just create one more, which will say it updates correctly, and we are going to add an async function. And to make sure that I still have access to this counter, I'm going to initialize it here as a key pair. So this is anchor, or let's say anchor.web3.key pair. And then I'm going to initialize it here just so I make sure that I'm using the same counter address. And this time I'm going to call, so let's just reduce this. Okay, so now I'm going to await program.methods. This time we'll call update, and we'll pass in the accounts, which are like the counter, which is the same counter that we used, and then a pair, which in our case is provider, same as what was there before, a public key, and then I'm going to do an RPC. Now let's see, so essentially it expects a new data. So in this case, let's just pass in 5 for now. So essentially we have called our RPC, and then let's just read the data again, and let's check what's the value this time. I'm going to do an anchor test. This will again run off the test cases. Is initialized as fine, updates correctly is fine, and you can say that the count has been updated to 5. So this is it for this video. In the next video, we'll start to look into the actual staking contract and take it from there.